Hey guys, Cash Cho with Choate Engineering Performance, and we are back at SEMA 2023 in the Mahle booth with Dan Begle, who is the engineer for, very much so the engine bearings and the products that Mahle produces. And Dan has a long pedigree in the performance world, dating all the way back from when Henry Ford first came out with the Model T. No, in all seriousness, Dan has been in this industry in the NASCAR world with Roush Yates and Doug Yates and the racing and all right, so I'm going to get Dan just to give a quick snippet of his long tenure in this company and all the experience that he has, because he is just a wealth of information and a really, really good friend of mine. So take it away, Dan.
Cass, thanks. Racing has always been a big part of what I do. I started racing when I was a young child. I was too small to lift a tire up, but for some reason they drug me around. I guess they thought I was someday going to be something. I don't know.
Boy, were they wrong.
They were so wrong, but I enjoy doing what I do. I enjoy talking about how I've been very fortunate. I worked Jasper Engines, diesel room. Then they got involved in the racing, and I look, I'm going to do hospitality just so I can be at the racetrack. And one thing led to another. Got involved in NASCAR, started in 1990, and did all kinds of jobs from sweeping the floor to owning my own shop. And I got a call from Robert Yates and to go work there, and worked at Roush Yates for 13 years. I was an assembler, engine assembler, dyno operator, everything, track tuner, et cetera, et cetera. Robert wanted me to shut down my shop that I had owned, and I thought, wow, this is a pretty cool opportunity, to go work for Robert Yates.
Yeah,
so
when he calls, it's
like I stopped what I was doing, and but it was fun. So I went there, and about 4 years in my tenure there, I became the reliability engineer at Roush Yates. So what I'm doing there is looking at parts that have raced, and I would give a report to engineering and production of the health of the engine on Thursday, what raced on Sunday. And it was so fun because I got to help develop the 2 race engines, anything bearings, pistons, the entire component, belts, you name it, durometers of O-rings on dampeners, et cetera, et cetera. And I was a reliability engineer for 9 years. And now I came to work at Mahle, and I get to take all that experience and all the dynoing and all the stuff I saw go bad and good, and why. I work with the engineering with Mahle, manufacturing, and understanding the basic engines a lot deeper. And now I'm working with engineering, working with manufacturing of how parts are made. Bearing, when I came to Mahle, said, we want you to be the bearing guy. So I took that to heart and ran with it. And I put in thousands of bearings in my life, just like a lot of engine builders. You're snapping a bearing in, the old saying, it's just a piece of stamped steel, right? And then I got involved in what really is different on bearing, and what makes bearing a bearing, and oil flows and loads and everything. And it's very interesting.
Bearings are such a deceitful piece of material, a deceitful component of the engine. You think it can be so easily misunderstood and, oversimplified by so many people so many times.
Sure.
There's so much more going on in the bearing. And so for the guys that have been watching and keeping up with this, we are working right now with Cody Pulliam on a Duramax build, and Mahle's going to be working with us. We've got some pistons that we're working with them on, and also the bottom end of the engine. And everything about an engine is it's just a complete system.
Absolutely.
And if one portion of that system does not operate correctly, it really doesn't matter how good the other part is working. Right?
It always finds its weakest link, right?
Exactly. So, when you're putting that kind of power down, 2,500 plus horsepower, that's going to take its toll on the whole bottom end of that engine. And having stock bearings is just obviously not an option. It's not going to hold up. It's not designed for that. So while we're kind of on the topic of why it wouldn't hold up to that, tell me a little bit about the approach from a stock bearing to a performance bearing, kind of some of the things that are different about that.
Yeah, stock bearing is great. You have X amount of horsepower on there, and the manufacturer comes up with this, and then when you add power, When you add power, you're adding more flex into the crankshaft. When you add more flex into the crankshaft, what you set your oil clearance to in the shop at room temperature versus operating temperature with a crank that's wiggling around because you're making more power, it changes your oil clearance. So, it's like, okay, not a big deal. Well, it is a big deal because, a typical engine, we have 50, 70 pounds of oil pressure, right? And we talk about oil pressure. Well, when a bearing has a bearing design, the eccentricity is different. The material's different between a stock and a performance. So as you're doing this, the performance bearings carries more pressure between the crankshaft and the bearing to keep it from coming in contact. So why that's important on a performance engine is because you get more crank flex, you get more pressure loads coming down, and you need more film pressure to keep the shaft and bearing apart than you did on a stock design bearing with a stock horsepower. And when that film pressure, if you would run a stock bearing, you don't get the film pressure, you're going to have contact and you're going to have a bearing seizure failure because you lost oil pressure in the bearing, not oil pressure in the engine. Film pressure, which is a huge difference. Yes.
Yeah, it's so interesting when you start looking at these things. You think that you're looking at your gauge at your dashboard and everything goes okay, everything's good. Again, we were talking to Eric a little bit about this earlier, and what static and dynamic differences are completely different. And a lot of times when you're looking at a crankshaft, we talk about the twisting force, the radial forces that are actually the torsional loads that are being placed on the crankshaft. But I've seen a lot of the FEA that he provided over the different presentations and things. The neat part about it is most guys would think that crankshaft would lay inside the bearing, right? And it's twisting, but all the twisting that is taking place is like this.
Absolutely.
But it's not.
Yep.
So what you're seeing is flexing this direction as well.
Yeah. So in saying that, we dampen off of total twist, but the engine is bay to bay. You have a main bearing and you have a rod, and what you're getting is this. Well, as the crank is loading and angle is twisting, the clearance that you statically set in the shop now is less because you have tilt on your main. So when you have tilt and you have the twisting, it compounds from here, take clearance to what we call orbiting. And when orbiting that's when the film pressure goes away and you start having contact. So in saying that, you have inline engine, you would think all the force is going down.
Right.
You have a V8 engine, it's still going down. Right. But as it's orbiting and things are flexing, you find that it's going up and down. So you can actually have a force load on an upper when you look at it and you're like, well, what happened? Well, it's because the crank's flexing, you lost that film pressure. A film pressure on a given engine, it could be somewhere in the excess of 20,000 psi. So you take 20,000 psi, and when you crank flex, it hits it, so the film pressure spikes. But what happens when you run out of the film, because the pressure spike, it dissipates. Now you have no oil between the bearing and the crank, which causes frictional heat, which causes the failure.
So we saw some testing, I think, from Sabre, and for the guys, I think that's right.
Yes.
So for the guys that don't know what Sabre is it's basically a software that is proprietary to Mahle that allows them to see what's going on in a computed state to find out what the fluid pressures are. And I remember we were talking about some things, and we saw, I think it was 54,000 pounds of pressure.
Yeah, it depends on the application and what it is, because the more horsepower, a diesel's make a lot, the burn time is different, and you have to create enough film pressure to offset that burn time and the pressure that's put on there to keep oil in the system on the journal.
So that, and I'm going to reiterate what he said, because if you weren't paying attention, you would have missed this. It's not enough that you have the supply of oil pressure going to the bearings from the oil pump. It's actually the film pressure is what he's talking about. Oil pressure, as we know it, we think about it, is in terms of from the pump to the journal itself. But now that we're adding these dynamic forces from different combustion events, now we are compressing this fluid and actually in some cases sending it back the opposite direction.
Absolutely. Yeah. In saying that, as the crank is turning and you get a high pressure, and back to you have 75 pounds of oil pressure, let's say, and you're taking 20,000 pounds or 30,000 pounds of oil pressure as that's flexing around, it's not only trying to get out, it's also trying to go back feed to the oil pump. You know, and another thing we found, I mean, simple things. The crankshaft condition, chatter.
Yeah.
You get chatter, which creates pressure spikes as it's going around here. And every time you have a spike in pressure, the residual of a spike in pressure is a low pressure film right after.
Yeah.
Because the pressure spike was the pressure, the oil getting shot out.
Right.
So now it's deprived right after that. So the pressure, the failure mode typically comes right after the spike.
Yeah. That's so interesting. It's almost like a low pressure area of, it's like a storm front coming through, you know.
Yeah.
You have a high pressure area, and then right behind it you have this low pressure area, because there has to be something that's taking up the place of this. And that's so interesting, because a lot of times, you know, you're looking at bearings and you're seeing wear out on this side here, wear out on this side here, and you're going, wait a minute, now I measured the taper. There's no taper in that journal, but that all has to do with the flex that's going on with that crankshaft.
Yeah.
And so for that reason, there's a lot of things that have to be happy. You know, it's a lot like what Billy Godbold talked about. You know, what the camshaft does, and the relationship between the camshaft and the valve train is a lot like Ginger Rogers and Fred Astaire, except they have to do everything backwards and in heels kind of thing.
Yeah.
And so it's a lot like that with the crankshaft and the bearing, the relationship of the oil film. And so that's really, really important. For us to be able to make the kind of power, though, that we're looking for, what do we need to do?
So, I mean, the big thing is, one of the things you're looking for is you got to say enough clearance to know when you do have the flex of the crankshaft that you don't completely block off that oil. So you need to set clearance. And now what works for a stock may not work for a higher performance. What works for this crankshaft may not work for it. You mentioned Saber Fit. Okay, and Saber Fit's a wonderful tool if you have a specific engine. As an OE, when we are large OE you know, we do a lot of bearings, a ton of bearings for OE, and we know exactly what that engine's going to do: combustion analysis, the environment, the oil, et cetera, et cetera. And it's like, it's easy to define a bearing.
Yeah.
You know, we're as someone told me one time, we live in the wild west. We're trying to make something, but we have a lot of unknowns.
Exactly.
And you know, so in saying that, what you run this particular crankshaft, and you know, you're diesel, but I see it in the gas world also, and it's like, well, it's the same thing, different crankshafts, so totally different responses. All right, everything's the same, but the shaft, counterweight location, balance, you know, the chatter, the smoothness on there. But you know, at the end of the day, is like, you have to know that you're going to have more clearance in there, because of in the higher performance, because you're going to have crank flex, and you need to be able to have enough cushion that your film pressure can go up, but you don't make contact, so the film thickness diminishes. Right. So you have to have more clearance. So then the next thing is, there's always that what if.
Yeah.
You know, the situation, temperature. You know, we got the super tune on. You know, whatever it might be. So a bearing is going to have failure when the overlay material exceeds the melting point of the temperature. So typically it's a copper tin lead. So you look it up. You know, the melting points of the tin and the lead are the lowest. So you get friction temperature, 420 degrees, you start sweating out, melting out that element. And once that happens, bearings don't self-heal.
Right.
Once they're done,
they're done.
They're done.
Right.
You know, there's no Band-Aid, there's nothing you can put in the oil to fix it.
Right.
It starts melting out. Well, when that starts happening, now you're starting to create a seizure zone, and it can continue to snowball from there. So, you know, that's the big thing, getting clearance. You know, people talk about coated bearings.
Yeah.
What's the advantage of coated bearing? Do I need a coated bearing? Well, coated bearing, I always say it's kind of like insurance. If you have health insurance and you never go to hospital, you paid a lot of money for nothing. But you ever go to hospital, and you're pretty glad you have it. So a coated bearing is really cool, because it's creating a thermal barrier. One thing it does is the thermal barrier. So it shields the plating, the elements of the plating, from the temperature. So it's creating a thermal shield. The other thing is it's a Mahle base. So talking about Mahle, it's slick, right? So when you lose that film thickness and you have contact, the Mahle is a dry film lubricant that will help keep that temperature from escalating. So it decreases the temperature in the bearing because it's slick. And it will help keep the thermal barriers so you have less chance of having a failure. So, you know, I am a fan of a coated bearing from that aspect of knowing that you have put a protection barrier against the plated overlay.
You know, the more you talk about it and you explain it, it almost seems like when you're thinking about it, you know, we coat the pistons for the very same reason. It almost looks like your crankshaft is almost like your piston in some cases, and you've got a shaft that's running and the explosion event that's taking place on one end of the crankshaft and a pressure event that's taking place over here, but you also have the same down here.
Right.
And two things that are going on.
Right.
And a lot of the relationships that we see in the combustion chamber, you know, are actually very similar in terms of the pressure spikes and different things like that.
Absolutely. I mean, your piston combustion and you have movement, so the same thing's happening. You know, we have crankshafts, as we mentioned.
Right.
Block flex. You know,
Yeah.
we've had some discussion on block flex and opening up and all those things. Everything that will question that film pressure or thickness can play a factor on the bearing.
And I think that's one of the most misunderstood things. Most people think that a cast iron block is extremely rigid, right? And to some truth, there is some truth to it that it is rigid in a certain state. But when you start putting combustion events into this thing where there is timed explosions that are taking place, there's all kind of things that are going on with that block. The block is twisting and deforming, and that's the reason why we have to have certain materials that are able to, like for instance, head gaskets with multi-layer steel gaskets, is because it has, you know, obviously we're trying to separate the block from the head. It has to take up the void now between the two surfaces of the components. And that's a tremendous amount to ask for an engine. You know, the more you learn about an engine, the more you're amazed that it even runs down the road at all.
It's you know, and it's sometimes the things you don't see. You know, for instance, you know, this bearing, and we're going to jump back to the stock bearing and the performance bearing. You know, this bearing, it's like, okay, it's a tri-metal bearing. You know, a lot of people, what's a tri-metal bearing? Well, tri-metal bearing is free, so you have a steel backing. You have what's inside that you don't even see. You have a copper tin lead substrate with a plating over top. So I always tell people, it's like, well, what's the difference in a bearing? You know, and some of it is like, if you go to a restaurant, you order a sandwich, you have a bun, a bottom of a bun, and it's the meat in between that you never really see, but that's the flavor.
Yeah.
That is the flavor. I've had some really good buns sometimes, but you know, but that's the base of the meal, is the meat in there. So in this case, we have a tri-metal bearing, copper tin lead. Now there's differences. There's a sintered bearing, which is copper tin lead, that's basically in a it's put in a container, it's mixed together, it's poured on a strip, it's heated, and the sintering part is rolling it and smashing it down. And then on the Cleveland bearings, we own the facility. It's in Ohio where we make it the strip, and it's a cast bearing. So you take the same percentages of copper tin lead and you melt it. Copper melts at 1960 degrees Fahrenheit. So we heat this to about 2,000 degrees. So you take the copper tin lead and now you have three elements that you have melted to make an alloy. Alloy of copper and tin is bronze. Okay, so you created bronze rather than having three elements. Now you have an alloy of copper and tin, bronze, and the lead is, well, let me back up. As a copper and tin bronze, as it cools, it will create grain structure. So the grain structure is the support for the overlay. So it's the meat in the sandwich you don't see is why the bearing becomes more rigid. So by creating grain structure of taking the elements and making an alloy, you get better adhesion and you get grain structure, which creates strength. Right. 20 to 30% more strength.
No different than the forgings that we were talking about earlier.
Absolutely.
Right.
Absolutely. So what's the lead for? Okay, as you have grain structure, back to your storm, stuff moves around in the storm, right? You want something to dampen that movement. The lead doesn't become part of the bronze. It's the filler between the grain. Right. So as it fills, as the grain is moving, the lead is dampening that. So it allows movement, but doesn't go too much movement. And that's how you build strength into that. So there's a big difference in what bearing you put in. Even though cosmetically, you don't see the meat in the sandwich.
Right. You know, it reminds me of a commercial, you know, back in the days of Wendy's. to borrow off of your bun-to-bun scenario. There's so many bearings out there, and you have to ask the age-old question, where's the beef?
Where's the beef?
Right?
Yeah.
But really and truly, that's what it boils down to, is what's, anybody can make a bearing on the back and the top, but what you're putting on the inside, that's what really, really matters.
That is really the thing. I mean, we go eat something, and if where's the beef? If it's not there, or if it's
you can use that later, by the way.
I might use that one later. If it's not tasty, it doesn't taste good. If it's not strong, it's not going to work as well. So when you're making big power numbers, or even and sometimes it's not even the case about a big power number. Again, my background, I was a reliability engineer at Roush Yates, and everything was about making power, but it needs to be reliable. And when you put your name on the valve cover, you want as much reliability in that engine for your reputation.
Exactly.
The meat in the sandwich, in this case the substrate, is what's giving you that margin of reliability, because it's a stronger bearing. So regardless of what happens, because once that engine leaves your shop, you can't control what happens to it, what he's pulling, what conditions he's in, overheating, whatever, everything you want to build reliability and margin in.
So as far as the production bearing of, we're going to be looking at an LML Duramax, right? So if we were to compare the load rating of a stock bearing versus what we're looking at putting in to Cody's engine now, what kind of numbers could we say?
Oh, I think it goes back to the Sabre. That's a really loaded question, because again, we're OE, and the Sabre, as you mentioned, we do combustion analysis data on that. Back to the same thing, we live in the wild, wild west.
Right.
So there really isn't a lot of testing to say, this is what numbers you're getting. So for me to put that number in there is I have to caution what I say here.
Sure.
But for your case, or anybody else that's building these engines, it's like, look, I'm going to get the best part I can that's available to put in there to hold up to that kind of pressures that are going on, that much crank flex that's going on. I mean, there's a lot of stuff, block flex, back to the block flex, all those things. Because if something's moving, whether it's crank, whether it's block, power, whatever is moving, all the bearing knows is what you set that clearance to.
Right.
And it doesn't know where it's coming from. It just knows I don't have what I thought I had, and now I'm going into failure mode.
Yeah, the funny part about it is if you think about it, so the guy that manufactures the piston and the ring, right? He's always blaming the guy that does the surface finish on the cylinder wall, or the piston manufacturer blames the ring guy blames the piston manufacturer, the guy that everybody blames the engine builder, right? And then this is only part of the equation. So we've also got, like you say, the crankshaft chatter, not just the crankshaft chatter or the surface finish of the crankshaft, not just the torsional loads and also the flexing of the crankshafts in different planes and environments, but also, again, Randy, Neil, y'all talk a lot and work a lot together with trying to keep and capture the chaos, really, that's taking place with the crankshaft itself. So balancing the crankshaft, making sure it's happy, because even it doesn't matter how good the bearing is, if the relationship between the bearing is compromised due to the orbiting of the crankshaft and things that we could have done for that,
right? Or
the oil is an issue now, because there's so many things that are affected by the next thing, and if it's touching it, it's affected by it.
Absolutely. I mean, and it's one thing, again, because it's impossible for you, back to your question statement, it's impossible to say, well, what kind of cylinder pressure? That's possible. Is it feasible to say, I'm going to run data analysis that we can cut the perfect bearing for that?
In a perfect world.
We could.
Yeah.
But the cost to do that is prohibitive, because that's what big money from the OEs do for that. So we have to just build margin, knowing we have the best parts in there. And that's one of the things I work on, is different overlays and what we can do. And again, it's a part, but every part, and that's why me and Randy got connected on that, is when it's a part until it goes in the engine, now it's a system.
Exactly.
And you have to look at system.
That's exactly right.
And I mean, you had some conversations on failures, and you think this is a failure, but that's like the third thing that happened. And that was just finally the straw that broke the camel's back, but it came way back here from part of the system. So it's understanding the system, thinking out of the box, stretching
Yeah.
yourselves, and I know we've had some great conversations
man,
on those
yeah.
in the past, and that, it's really cool stuff.
Yeah, the more you know, the less you know.
Absolutely.
And I mean, that's the fun part. That's also the frustrating part.
Yes.
Yeah, man, I greatly appreciate your time and willingness
Absolutely.
and expertise. It's always a pleasure working with you, and I'm
Same.
excited about working on this project, and also for the guys on the Diesel Masters. If you haven't checked that out, you can go to YouTube, check out Chode Engineering Performance, look under Diesel Master. You'll see there's a couple of different, we're working to upload more episodes, but we're in the process right now of setting up for success for the land speed record. That's actually pulling a trailer with a Ford Excursion.
Be awesome.
And that's kind of how we met, with your old 6-liter that blew the bearings out because of lack of oil from, and unfortunately this happens a lot of times. It wasn't because of, you in good faith took it to, I won't mention obviously the shop, the repair facility, but they didn't do their job.
They did not.
And so because they didn't do their job, the bearings failed on the factory engine, and we that's kind of sort of our first collaboration, I guess.
Well, to that point, again, the bearings failed, and then you did a great job. You're sending me pictures, and it's like, hey, the bearing was a secondary to the problem that we figured out, and
yeah,
I still use those as the worst set of bearings I've ever seen in my life, and they came out of my vehicle. It's pretty bad.
Who would have thought a bearing needed oil, right?
Yeah.
But anyways, so we're looking forward to this. Thank the guys so much at Mahle, and so excited about these projects.
Appreciate it, guys. Thank you.
My pleasure. See you guys later.